What's up, everybody? Hope you're all doing well. Today we're going to be looking at a kind of classic mass connected to a pulley problem. So it basically looks like this. Here's our pulley. We're going to stick a mass on it and let it go. So we did some of these as Atwood problems where we had kind of two masses in the past, and we will get to that, but for now we're going to just stick with one mass. Alright, let's go ahead and jump right in. So here's the problem, and as usual I would encourage you to see if you can solve this on your own before I solve it, and then come back and see if you get it right. So we're ultimately we're looking for what's the final velocity of this mass when we let it go. And this is attached to the pulley. I'm not sure if you can see this, but we have this kind of attached to a pulley, so as it falls it's going to start to rotate the pulley. So the first thing we're going to do is do our free body, and we're going to do it on two objects. So the first one is we're going to do it on the mass. So the mass that's falling, we have the weight here, right? Or we'll just call it mg as it's falling. And then we have this tension in the string up here, so we'll call that t. Now we are going to be accelerating here, so I'm going to draw the downward weight greater than the tension. And then the tension up here is going to pull back on the pulley, right? And since it's a single string here, these two tensions should be the same. So this will be T here as well. So that's step one. We do our free body. Step two, then, we're going to set up two summations. So the first one is going to be on the falling mass. So that's just, since it's just kind of linear, no rotation here, that's just a force summation. So remember, our direction of acceleration, we're going to define that as our positive direction. So in this case, we have mg of the mass, falling mass, mg, minus the tension coming up, and that should equal ma, where m again is the falling mass. Why don't we call that, since it's 2, why don't we call it m2, m2? Because we're going to also have the mass of the pulley here to deal with. So let's do the mass of the pulley. So the mass, the pulley is rotating, right? So it's rotating. So this has an angular acceleration. And so with this, we're going to sum up the torques. So we're going to say the sum of the torques. So in this case, we just simply have the tension times the radius of the pulley, right? So this would be R, because it's torque, it's not force. So you have the tension times the radius of the pulley, and that's it. Right, that's the only thing rotating the pulley here. So that's going to equal I times angular acceleration. So that's the two main equations that we have. Now the acceleration and angular acceleration are related to each other, right? So this, right at this point, let me do a different color here. Right at this point right here, there's a certain acceleration, linear acceleration, right? And it also has an angular acceleration as well. And those two things are related by a linear acceleration equals r alpha. So we're ultimately looking for v final. Notice if we can find the acceleration here, then we can use some good old kinematics to get v final. So let's go ahead and make some subs. The first sub we'll make is in here. So we're going to go I. So remember, this was a solid disk somewhere. Where does it say? Yeah, right there, solid disk. So a solid disk, the equation is 1/2 m, and this is m of the pulley, times r of the pulley squared. And then alpha, when we make this substitution here for a, we're going to get alpha is equal to a divided by r. So notice what we have here. We can make some cancellations, right? So one of these r's is going to cancel with one of these r's, and then this r over here is going to cancel with this r over here. So we're left with tension equals 1/2 the mass of the pulley times the acceleration. So the last thing I'm going to do is substitute this tension into here, and then solve for the acceleration. So let me make a little bit of space here. Go like that, there we go, and then we'll go ahead and finish this up. So when we substitute that in, we get m2g minus, make the subs, this is 1/2 mass of the pulley times A equals M2A. Let's go ahead and get this over onto that side. We'll do the algebra. So M2G equals M2A plus 1/2 mass of the pulley times A. When we distribute, we get A M2 plus 1/2 mass of the pulley equals M2G. And then lastly, let's do this over here, finish it up. M2G divided by M2 plus 1/2 mass of the pulley equals A. So I'll leave it up to you to substitute and solve in the numbers. When I do it, I get 4.9 meters per second squared. So that's going to be my acceleration, right? The acceleration of the mass going down. So that's not actually what we're looking for, but we got to get that before we can get the answer. So let's go ahead and solve this whole thing. Let me shrink this down here. So remember, this was equal to A. So at this point, we just have a simple kinematics problem, right? So our V initial was 0. This is of the mass. The distance it travels is going to be 3 meters. And then we just found the acceleration. And we are looking for V final. So we'll use this equation, Vf squared, Vo squared 2A times the displacement. And I guess I'll do this one, Vf squared. So V initial, 0, 2, we'll use the acceleration we just found, and 3 meters. So solve that, and I get 5.42 meters per second. So that's the mass connected to pulley problem. Now I'm going to point this out. There's a secondary way you can solve this problem, and that's using conservation of energy. And we will learn how to do this, but if you already know, if this is just a review video for you, I would go ahead and jump over. I did an identical video for like this, using all the same numbers, but using conservation of energy. So I'll link to that down below. All right, hope that helps. Please let me know if you have any questions, and we'll see you in the next one.